Okay, well, nothing better to do than to deliver another example. This one will be on the air standard Otto cycle. This problem 38 from chapter 9 from some book, and it says there's an Otto cycle compression ratio of 9.5. I've also clipped the PV diagram for the Otto cycle, and you'll recall that the compression ratio is the ratio of this lowest volume. This is a PV diagram, so this is volume 2 equals volume 3. That's the ratio of the smallest volume to the largest volume is 9.5. It says prior to the isentropic compression process, air is at 100 kPa, 35 degrees C, and 600 centimeters cubed volume. So prior to the compression, of course, he's talking about state 1. Temperature at the end of the isentropic expansion process is 800 K. So he's given the temperature at state 4, the end of the isentropic expansion process. Um, yes, now he asks us to solve this problem using specific heat values at room temperature. And usually when they say room temperature, it means 300 degrees K. So you can just look those up in the table. So he wants us to find the highest temperature and pressure in the cycle and the amount of heat transferred in kilojoules, heat transfer in kilojoules, and the thermal efficiency and the mean effective pressure. Okay, so the maximum temperature and pressure, it sounds like we need to find state 3 because clearly that's the maximum pressure. And it also turns out that's after the heat addition. That's also where the highest temperature occurs. I don't have the TS diagram here to go with it, but we could see that the highest temperature is also at state 3. So just right off the bat, the way this problem is described, we know everything here at the beginning, state 1, and we know this compression ratio, which is very helpful, but we don't know anything about state 3. He gave us some information about state 4. So it seems like we're going to have to work backwards from 4 and forwards from 2 to find this state 3. So let's see if we can stumble through it. So he says assume the properties constant at a room temperature. I think I'll still look this up. Let's see, I may not have this activated. Let me go back and yep, my add-ins. I need to get my ideal gas add-ins working here just so I can look this up. So now I should be able to do this. So CV air, and I'm going to put 300. And the units are kilojoules per kilogram per degree K. We probably will need this ratio, and I'll just calculate it. I think there may be a I don't think there's a function for it. We're just going to have to calculate it. So it's the CP ratio at 300 divided by the CV. So that ought to help. Okay, and it's 1.4, and if we'd been thinking a little bit harder, we would have come up with that. So um, those are the properties, and he wants us to treat those as constant. So let's see what needs to happen. We know the given temperature T1, he says, is 135 degrees C. So I'm going to go ahead and write that as given information, but I'm going to put it in degrees K. He also gave us the initial pressure, which was 100, and the initial volume, which he gave us in centimeters cubed. I'm going to struggle a little bit to get that sorted out, but it's 600 centimeters cubed. But let's see, 100 centimeters per meter, and I would have to cube that to get centimeters cubed per meter cubed. So that's a small number, but that's in meters cubed. Okay, so that's our given information. How do we need to go? Station to station is the best way to travel. So let's see how far we can go going from 1 to 2. We know process 1 to 2 is isentropic. And for ideal gas with constant specific heats, we can calculate T2 as being related to the volume ratio, which I didn't write down here, but I need to do that. The R ratio was given to be 9.5, so we will definitely need that. And by the way, that's equal to, it's given, but R is equal to V1 over V2, and it's also equal to V4 over V3. And we know that from the diagram and the definition of the specific heat ratio. Okay, so back to this calculation, we can find T2 from this ratio of V2 over V1, which you'll note is 1 over R raised to the 1 minus K ratio. And that's T2 over T1. That formula there gives me T2 over T1. I need to multiply times T1 to get T2. So I expect T2 to be more than T1 because of the compression, and so it means I've gone in the right direction when I get a number that's bigger here. So that's good for T2. We could find V2 if we needed to. I'm not sure if we do. Let's see what we can figure out about. Yeah, we need to find all the pressures. So what about the pressure 2? Let's use our ideal gas law. And yeah, I'll try to insert a formula here. Been having a little bit of trouble to get those to appear where I need them to be, but okay, so we would write something like this, that P1 V1 over T1 is equal to same thing. We need to break that up, don't we? That's not equal to pi r squared in spite of what the equation says. It's equal to the same thing at state 2. And so what do we know about this process? Well, I'm getting ahead of myself, but this process is isentropic, and so this ideal gas law won't be as useful for us here. We could sort that out, but we can get it from the temperature ratio, and we'll hold on to this because we're going to use it in just a minute. So I apologize. To find that pressure 2, we can find P2 from the temperature ratio. In other words, for an isentropic process, T2 over T1 raised to the K over K minus 1 is equal to the pressure ratio. And so if I get all of this straightened out, I think we'll be okay. Yeah, let's put that like that. And that's just using the isentropic relationships that we reviewed before about the temperature ratios and the pressure ratios. And we can use those when we have constant specific heats. Okay, as I said, I was getting ahead of myself a little bit in this ideal gas law. When we go from state 2 to 3, what do we know? Going from 2 to 3, the volume is constant. So that's what I'm trying to look at here, is if we can find pressure 3. Can we find that? I'm not sure that we can, but if we wanted to, we could try. So in going from 3 to 2, the volumes are constant, and so we do know pressure 2, and we know temperature 2. If we could somehow find temperature 3, we could find P3. How can we find temperature 3? Well, without having any knowledge about Qn, we can't find it from here, from 2 to 3. But again, looking ahead to 4, we know the temperature 4. So we can find temperature 3 by using this isentropic relationship. So he said temperature 4 is 800 degrees K, and I haven't recorded that. And so let's see if we can piece that together then. So we look at process 3 to 4, we can find T3 from the ratio of V3 over V4, which again is 1 over R, raised to the 1 minus K power. And that relates that to T4. So we find out that it's 1970 degrees K, and with that then we can turn around and calculate P3 from P2. So it's equal to P2 times T3 over T2. I'm just using this ideal gas law with V3 equal V2. Okay, so we got the pressure and the temperature there. He wants to know the temperature at 4, so how can we find that? Sorry, the pressure at 4. And again, use the ideal gas law for process 4 to 1, which is a constant volume process. So we can find P4 from P1 times T4 divided by T1. It's the same relationship that we used right here. So the pressure there is 259 kPa. Okay, so I think we found all the pressures and temperatures that he wanted us to have. He wanted to know the amount of heat transferred in kilojoules. Oh goodness, so in order to do that we need to calculate the mass of air that we have. And we can find that from the given initial condition. At state 1 we know the pressure, the volume, and we know the temperature. But we need to know the ideal gas constant. Yeah, I'll just do it this way. But that gas constant is equal to 0.287. And this will give us in kilograms. So now that amount of heat transfer is just going to be equal to the mass of the air times the specific heat times the temperature change. Okay, so we've got that. Thermal efficiency. Well, we're pretty close. I mean, we can either find QL and calculate that way. We can do that. This is going to be exactly the same formula, except, of course, we're going to have the heat rejection process involved here. And once we've got QL and QH, we can always find the thermal efficiency as one minus QL over QH. Says it's about 59%. Now, since this is the ideal cycle with no irreversibilities and constant specific heats, we can also calculate this from the check it from the formula, which was I don't know, I'm going from memory here, which is bad. We'll have to go flip through the book. This is raised to some power, but I don't remember what it is. So we'll take a quick look in the book here, see what he tells us. Oh, there it is. 1 over r to the k minus 1. So 1 over r to the k minus 1. And yep, that gives us the same answer, so we should feel good about that. And we could use either way. The last thing he asked for is mean effective pressure, and we haven't talked about that yet, but that's the average pressure that you would need to generate the same net work um, by expanding through the volume ratio. So and again, there's a formula in the book, but it was in the review part and I skipped over it, I think. Yeah, mean effective pressure is the net work divided by the delta volume. So we need to know that Vmax minus Vmin, and we've got that mercifully, so let's see if we can come up with something. So we need the net work. So how much is that? It's equal to QH minus QL. And now the mean effective pressure is equal to the net work divided by Vmax minus Vmin. Well, that's going to be the initial volume. Didn't we calculate this somewhere? No, we didn't. But anyway, Vmax is equal to 9.5 times V1, and then we need to subtract off V1, so it's going to be R minus 1 times V V1. And let's see what we come up with here. And I'm almost afraid to look, but we've got some answers to compare to. How'd we do? Let's see. He said should have 1969 degrees K and 6072 kPa. So we got 1970 and 6094 kPa. So I think we probably had a slightly different value for the specific heat. Is my guess on that. 0.59 kilojoules, 59.4%, and 652 kPa. So we got the 0.59 for the thermal, 0.59 for the QH, 59% for the thermal efficiency, and we got 68.6 for the mean effective pressure. So again, yeah, so I don't like that answer. He's got 652 kPa. Everything else we're pretty good on, so let's see where we may have gone wrong. I'm assuming it's in this volume ratio calculation. Oh, yeah, I guess I've done this just backwards. Yeah, let's think about it. The initial volume is the largest volume, and then the next volume is the smaller volume. So I guess this is 1 minus 1 over R times V1. Yeah, let's try that. Yeah, we get a much more better answer. Yeah, the downfall in my thinking there is I was considering V1 as being the smallest volume, and that we had to increase to V2, and that's just the opposite. We need to compress to V2, and I needed to find the difference between V1, that's the largest volume, and V2, which is the smaller volume. So he got 652, and we got 651.8. All right, well, that's it for this example.